Welcome everybody to our little coffee clutch this morning. I know it's early, and I appreciate that you all made it in. I'm convinced that this being the slightly less technical of the two sessions this morning, that means that all the early risers are next door, and the folks that are here were out late last night. So I really even extra appreciate that you made it here this morning. We are here to talk about what does it look like to unlock the expansion of the grid to facilitate new large loads. I'm going to first introduce our panel, and then I'm going to say a couple of things, and then quickly turn it over to the panel to walk us through their perspectives on what's going on in this space right now. Just going down the row, Karen Onaran is President and CEO of ELCON, which is an association of the largest energy consumers in the U.S. Elliott is VP of Commercial Projects at Constellation Energy, which is the largest operator of nuclear power plants in the U.S. and I believe the largest server of competitive retail loads in the U.S. still as well. To his right is Moorty, who's Principal for Market Design and Development at ERCOT. Thank you again for making the long trip over from Taylor. And down at the end of the row is Michael Walsh. Michael is here representing RedoxBlox and Grid Zero AI, and he's going to tell us a little bit about what's going on with industrial heat as well as some other areas of growth. Before we get started, I just want to say good morning, and I really appreciate everybody coming to this session. As a member of the board at ESIG, I recognize how important the role is that we play as an organization to help drive knowledge forward on what's possible, and to try and make sure that we're correcting the record when things get out that may sound right, but actually technically we can do better. And I've seen ESIG do that from its founding, and I'm just appreciative of the chance to be part of the board to support the mission. That's really what this panel is about correcting the record to a certain extent, and also talking about what's possible as much as what's reality right now, and maybe why those two aren't lining up quite as fully as they could. I'm here moderating this panel based on my own background and experience. I spent 15 or so years leading markets and operations across both PJM and MISO. And then over the last few years until last year, I was leading energy at a relatively small company called Meta. And what I saw firsthand was this extraordinary explosion in growth of the demand for energy for data centers in particular, but also we saw it for other kinds of large customers, manufacturing and the like. And I recognized myself that this was likely going to be an untenable thing, and we've really run into the brick wall this year and late last year in terms of the ability to keep up with this exploding demand. And what that experience has shown me is that we really do need to invest in what does it look like to streamline interconnection processes, get the market incentives right. We've got to figure out a way to get large loads connected faster, because it is a block to growing the digital part of our economy and growing the resurgent manufacturing base as well. If we want to be able to do the things that are the wave of the future, we have to be able to electrify them. Electricity really is the key to that, and this is one of the key elements of how we actually unlock that kind of economic growth. Ultimately, the solutions are going to require us to think out of the box. I know that's a trite way of putting it, but I really believe it, that unless we're willing to change how we've historically approached things, in some cases invert historic practices, to think differently, where I am now at Verrus, we're going to be building flexible data centers, but there's no way to prioritize flexibility currently in our interconnection processes. So figuring out how to innovate around those kinds of historic practices so that we don't allow them to continue to be roadblocks is something I'm going to challenge the panelists to talk about today. to talk about not just what are the problems, but what are the solutions that we should be pursuing. And I'm actually going to be asking the audience later to help us bring those kinds of innovative thoughts forward to prime the discussion. So with that, I just want to say thank you again for getting here so early. I know it is still even a little bit dark out. Have the second cup of coffee if you need it. Go out and get it, bring it back. We're going to carry on and try and move the discussion forward. So with that, I'm going to turn it over to Karen. Thank you. Are you cute? Is she queued up?
Yep.
Okay.
Okay, now it's on. Well, good morning, everyone. Thanks again for joining this morning, especially if you were out late last night. I, however, was in my room with a bottle of wine watching Real Housewives of Beverly Hills. So my party days, I think, are behind me. So I appreciate those that actually went out and enjoyed Austin last night. So just to remind everyone, I'm Karen Onaran, President and CEO of ELCON. If you are not familiar with ELCON, we are the National Trade Association for Large Industrial Consumers of Electricity. We're mostly manufacturers, other large, production facilities. We do not currently represent data centers. They're a unique challenge, but my goal here as the first panelist this morning is to kind of give us a level set about what we're talking about co-location, why we do it, what are the challenges, what are some of the benefits of co-location. So, co-location and large loads seem to be the shiny objects right now that everyone's kind of focused on, but we really have been co-locating for decades now. The industrials have been using combined heat and power, combined cycle. So, we're kind of the grandfathers of this co-location idea. The idea of using waste heat and putting that back into our production facilities, either through, electrical power or heating or cooling. So, we have been doing this for a bit, but we are seeing a transformation in large loads that require us to take a different look and maybe some different configurations of co-location. Industrials are increasingly electrifying some of their production facilities to either clean up their production or use some of the efficiencies that come with electricity. We also have brand new players. These are the big data centers. These are the energy hogs who are really looking at some of these co-location ideas and configurations to serve their enormous appetite for electricity. So this is why we're sort of taking a new look at some of the options for co-location and why we're actually looking at co-location as an option. So traditionally, back in the olden days, industrials, would look at CHP and other co-location ideas. And why did we do this back in the day? Well, there was the operational efficiency of co-location. If you're taking that waste heat, it just makes sense to then use that again in your operations. So there was some operational efficiencies there. There was also economic efficiencies. If you're using waste and putting it back into your production, you're saving money. So it made sense at the time. Also with reliability, if you have that on-site capability, you know that you can rely on it if there are challenging situations on the grid or with other supply chains, you know that you had that on your site and that you could rely on it. But what we're seeing now is there are new challenges for growing load. And so that makes things a little bit, more challenging from just, CHP. That makes sense. What we're seeing now is the pace of thermal generation retirements outpacing the replacements. We are generation hungry, as are the data centers, industrials. We use a lot of energy. And we're seeing that thermal 24/7 baseload generation being retired. The replacement, it does not operate entirely the same way because a lot of the replacement generation that we're seeing is renewable, which can be variable because it does rely a lot on weather conditions. Battery storage is still, keep trying to keep up and become commercially available. So we're just not seeing that generation appear when we need it and perform the same way for that sort of 24/7 operation. Also, we're waiting for that generation to clear those very long interconnection queues. And I think that we've talked a little bit about interconnection throughout this conference and know that there are issues there with getting that replacement generation even onto the grid. Then we look at the infrastructure challenges with transmission. It's estimated that we need, trillions of dollars in more transmission infrastructure, which is a massive, massive price tag. Also, the siting and permitting challenges that go with transmission means that we're just not seeing it developed quite quickly enough. There's also a lot of political resistance to transmission. If you go to the states, there's a lot of apprehension about having their constituents, their customers pay for transmission that they see they're not getting, or they perceive that they're not getting a benefit from. So even to the extent that we identify a transmission need, it is very hard to get those approvals. And then thirdly, we're seeing a lot more extreme weather. So we are seeing challenges on the grid. More frequent and prolonged and severe weather patterns, whether that be storms, whether that be wildfires, droughts. So we are seeing all of these challenges happening at the same time, which show unique challenges for large loads being able to get the electricity that they need. But there are also other drivers that, make co-location attractive to large load. Many of ELCON's members, as well as the data centers, have clean energy goals. And so they are looking to connect to clean energy. And sometimes that means co-locating either with a solar facility or a wind facility. So that's very attractive for co-locating. That 24/7 reliability, again, having that generation source right there at your production facility or your data center. You can rely on that. That's there for you. And you're not relying entirely on the electric system or the grid. That same thing with resilience. When we see these large storm patterns, it can take down the grid. It can take down some of these generation resources we've seen with some of the winter freezes, even here in Texas, of all places, where generation, the natural gas, these wellheads freeze and you can no longer get that generation. If you have something on site, you're better able to protect that system and make sure that it can survive in extreme weather conditions. So it does make co-location an attractive choice. And then cost also, if you're paying just for your generation source, you're not having to pay for infrastructure upgrades to serve your load. But I will say that the primary driver that I've been seeing for looking at co-location is timing. Co-location is just one option that large load is looking at to serve their needs. And the reason being, we talked about the interconnection queue being so clogged, so that generation is not getting to the grid fast enough. These loads are here today. Data centers are ready. They want to be up and running within a year, 2 years. And if they're not going to get their generation out of that queue, it could be 5 years. Then we talk about transmission. Transmission can take up to a decade because of the siting and permitting and the challenges that come with building large infrastructure. And so, data centers, large industrials just cannot wait for the grid to catch up to serve their needs. So they're looking at perhaps putting that generation right there so that they have it. They're contracting directly either with generation providers. They don't see the same infrastructure upgrades that may be needed, especially if they're islanded. So there's kind of different co-location configurations. One co-location configuration is completely islanded. You're not on the grid. You cannot take energy from the grid. You can't give energy back to the grid. You are completely isolated. The other co-location is, yes, you have your generation on site, but you are still connected to the grid for either backup power or sharing even your generation resources in emergency conditions. So really, I would say timing is the primary driver right now for why large load is looking at co-location. So what are some of the challenges we're seeing about co-location? Well, the narrative out there right now, why we're even talking about this at this conference is, we've seen a couple of examples, national examples of data centers looking to either re-energize nuclear facilities or they're taking facilities off the grid to serve their needs. And so there's been a lot of consternation and decidedly so. We should be making sure that we are doing this fairly. But right now, when you hear co-location, you hear, oh, that's a negative thing. And it's not necessarily a negative, but that narrative that keeps going around is that, this is going to increase costs for other consumers, either through higher generation cost, higher infrastructure costs, because those infrastructure are usually regionally cost allocated. So if a big data center comes in and needs transmission to get the power that they need, those costs for that infrastructure is spread across, in regional areas. And then there's the idea of the stranded cost. Say a data center or a large industrial comes and says, yes, we're going to locate right here. We need X, Y, and Z. We need this upgrade for the transmission infrastructure. And then they don't show up. And then customers, retail customers, your residential customers are then stuck with that bill. So these are challenges that absolutely need to be dealt with, but this is not the entire conversation about co-location. Another challenge is really outdated tariffs. I've had members go into their utility and say, we're going to co-locate. How do we do the rates? And they dig through their files and they pull out some tariff that was written on a typewriter. And that just does not reflect the reality of today. And so we really need to get our regulators to understand, what the different configurations are. How do we pay for this? How are the rates done? Utilities are also a challenge. Utilities make money by selling generation or by building infrastructure. And so if you go to your local utility and say, we're going to put generation on our site, we're going to connect to the grid, or we're either going to island, utilities are not always so excited about helping out. Because they make their money through the grid, either through selling that generation or those transmission distribution upgrades. So they're not as always welcoming when a large facility comes in and says that they're looking at co-location. There's also some question about state and federal jurisdiction. I know that FERC is currently looking at co-location very closely for a lot of the challenges that I noted at the top of this slide. But, we're talking about retail service as well. So that's sort of a state jurisdictional issue. And so there's kind of trying to figure out who really is in charge of making sure that that co-location is a viable choice for large consumers. So what are some of the benefits? BYOG, bring your own generation. So that's, bringing your generation with you. We're not talking about taking facilities off of the grid to just serve your load. We're talking about you contracting directly with a generation developer, supplier, that type of thing. So if you do bring your generation onto your site for your use and your use only, it does not add to the system constraints. If there are transmission constraints, you're not adding more to the grid and increasing those constraints. If you are connected to the grid, you can curtail if you're taking service. If there are emergency situations, they can, pull back on their production or transfer their production entirely to their on-site generation. So that is an asset that we can be very supportive of emergency situations. And in the same way, if we're mostly using our on-site generation in some emergency conditions, if we're talking about massive blackouts that endanger human lives, we can actually take our on-site generation, inject that onto the grid for use by other customers. And then finally, if there is the need for transmission upgrades, that type of thing, we are better positioned. We have the finances to finance some of those grid infrastructure upgrades or new infrastructure, so we can, help with paying for, because everybody needs transmission. It's not just large load. We, in order to benefit all consumers that are looking to electrify, who are looking, to expand, their communities. Everyone is looking for additional transmission. So just a couple of takeaways just to leave you with as you listen to my fellow panelists. Colocation is just one tool in the toolbox. This is not something that every large load is looking to do, every data center is looking to do. This is one thing we can do while we wait for the grid to catch up to demand. If you can pair this with surplus interconnection, demand response, grid enhancing technologies, this is sort of a stopgap until we get the generation online and we get the transmission upgrades that we need. Another thing I want to point out is not all large loads are the same. We do operate differently. We have different requirements. We have different operating characteristics. So when we go to our regulators, we need to make sure that we completely understand the needs of individual large load. A data center is not going to always act the same way that perhaps a steel manufacturer will. And so we need to understand that large load is not a monolith. We're not all the same. And so co-location can look differently. How we interact with the grid also looks quite differently. And then finally, when I talk about, co-location being, one of the tools in the toolbox, one of the stopgap measures as we wait for the grid to catch up, we really, implore our regulators to, yes, work with us to figure out how we can fairly co-locate, but really let's address those conditions that make co-location look attractive. Let's clear those interconnection queues. Let's make sure that we're getting the generation that we need, that it is operating 24/7, that it is plentiful. Also with transmission, let's make sure that we get transmission planning right. Part of that is on us because we need to get our forecasts correct. I know that forecasting large load is a huge challenge, which I think we've talked about a little bit during this conference. But let's look at transmission planning. Let's look at transmission development. Let's clear up those permitting and siting challenges. So these are the bigger issues that, yes, we need to make sure that these little outlier things about co-location are dealt with so that it's been fairly done. But let's focus on the bigger challenges, because ideally, large load does want to connect to the grid, does want to use resources on the grid and have the transmission infrastructure there. So with that, thank you very much. That's sort of the level set. And then my colleagues will go into a little bit more technical details on co-location. So thank you.
Thank you, Karen.
Hey, good morning, everyone. My name's Elliott Flick from Constellation Energy. And for those of you, oops, I'm sorry about that. For those of you that aren't familiar with Constellation Energy, we're the largest operator of nuclear power plants in the United States. We're also the largest generation operator in the US, and we generate 10% of all of the carbon-free clean energy that is produced in the US. One thing that we're very proud of right now as a result of our partnership with Microsoft, we've announced recently the reopening of what was previously called 3 Mile Island, which has now been renamed the Chris Crane Clean Energy Center, which is going to bring another 900 megawatts back to the grid in central Pennsylvania in order to meet data center demands there in the state. Additionally, Constellation is currently doing a number of power uprates at our facilities. You can see on the map, the white dots basically represent the location of our generation plants. We have 23 nuclear reactors, and we are increasing the power through power uprates at those facilities. Now, this whole session in the conference is talking about behind the meter and data center co-location. And so you may hear this term behind the meter, and what does that mean? I would say that that's primarily a term that we talk about in, for instance, the PJM market. You'll hear it called in the ERCOT market, private use networks. And as Karen mentioned, there's different ways that behind the meter type of data center co-location can be done. It can be either fully isolated, or it can be partially able to utilize grid services when required. And I'll talk about a couple of those type of situations here in the next few minutes. But the real reason for these type of behind the meter data center co-location opportunities that our company is driven by is a number of things, including speed to market for the customers. In general, we can bring into service a co-located load at one of our existing generation facilities about 2 years faster than going through, a customer going directly through the transmission operator or local utility to connect that load. Additionally, important for us as a clean energy provider in the United States is being paid and compensated for that carbon-free energy. And in the PJM market, EFEX is a tool that can be used, but also for companies such as Karen was mentioning, where it's important for companies' clean energy goals to provide clean energy, we can certify through a behind-the-meter type of connection that power, that clean carbon-free energy has come directly from a clean carbon-free emitting source without going out onto the grid and getting mixed up with, all the other types of generation of electrons that are out there on the grid. So some of the type of attributes that folks like when they're coming to us to interconnect large loads at a nuclear power plant, they love that we have excess land that can be utilized for their projects. High reliability. Typically, these power plants are built on waterways that have water access for transporting goods in and out. Rail access is generally available for being able to bring product in and out for their type of generation needs. And so the major companies that come to us to do co-location and behind the meter type of interconnections include primarily data centers. We've been evaluating putting hydrogen production facilities, CO2 capture type of facilities. So basically what I'm talking about are very large users of electricity that have clean energy goals that are seeking these type of applications. And what behind the meter in my jargon typically means is that that data center load or whatever the load is can be disconnected so that customer is not going to be taking power from the grid, but we can set it up so that they can have grid supported power if that's necessary. Now, some of the things that we found very interesting working with data center customers are the specific things that they're looking for when when they're looking for power. It's not that they just show up and say, hey, do you happen to have an extra, 5 gigawatts of power that we can utilize for some purpose? They actually are looking for shovel-ready type of projects. They want to move that fast. And so as a company strategy, we are going after making sure that all of that excess land that I talked about is actually ready to go. It's zoned, it's permitted. We are at a shovel-ready type of state for these type of projects. And over on the far right side of the slide is kind of like the pinnacle of what these data center companies are looking for. They want at least 300 acres of land where they can build out gargantuan type of facilities. Most of them are looking to build up to a gigawatt worth of data center facilities these days as they approach us. Clearly you have to be outside of the flood zone, right? Data centers aren't going to plunk down where they're going to end up getting flooded out and destroy their facilities. So you have to have the right areas for that. Wetlands have to have already been addressed. If you have wetlands, mitigation needs to have been taken care of. Zoning needs to be done in most cases. Many localities do not have data centers as a permitted use in those townships. And so we have to typically do not only rezoning of the land from, say, agricultural to industrial, but also quite a bit of work in order to do what's called a text amendment. Generally has to be done within the localities. And then you can see there that in general on day one that power is available up to at least 50 megawatts to start their project, and then going on up from there. Carbon-free energy, as mentioned here, many of the companies are incentivized looking for carbon-free energy, and so that's something that they can get from nuclear power facilities such as those at Constellation. So this first slide that I'm going to show here, and I know that there are a bunch of power engineers in the room, but for those of you that aren't kind of up to speed on what the drawing is showing, this is an example of a 2-unit reactor. This is a design that we have permitted for fully isolated use within the PJM market. And basically, you always have one or the other reactor operating, and so there's always this high reliability of power that's available to the customer. We've set up so that there is a set of circuit breakers that will open if, for instance, the power reactor goes out of service, so that the customer loses power on a single feed. That makes sure that, once again, we're not bringing power back in from the grid to the customer. And we have a cross connect here in the drawing, which allows power to be closed in cases where one of the reactors is out of service, so that the customer's load can always be served by the in-service reactor. Additionally, generally, these data center customers at the lower voltage levels inside of their facilities, they can switch back and forth between power sources when they have a dual power feed. So this is just a general high level of how we are managing fully isolated loads. And as an example here in this graphic, what I'm showing is that being fully isolated from the grid means that when the power plant is out of service in that top left box, there is no power being provided to the data center. Then in order to bring power into service for the data center customer, we match voltage and frequency with the equipment within the nuclear plant to that of the grid. The nuclear plant connects to the grid, and only after the nuclear plant is connected to the grid can the customer be brought back into service. And then once again, if for some reason the power level at the nuclear plant dips below the amount of load that's being requested by the data center customer or other large load, the load will disconnect in that case. So that's how a fully isolated load works in our design. There are, however, alternate designs which allow customers to take grid backup power, and in those cases, that has to be negotiated with the local transmission operator. This is just an example on a 500 kV system. Power coming in at the top from the power station itself. You have 4 circuit breakers, and then at the bottom, the power goes out to the grid. So excess power goes out to the grid when the power plant is running. And then over on the right-hand side, that's power going to the tenant. And we have the ability so that if the power plant goes out of service, the 2 circuit breakers kind of at the top of that ring bus open, and power is still able to be fed backwards from the grid to the tenant in this case. But you can set up your protective relaying such that it either will or will not be fully isolated from the grid in this type of a condition. And some of the customers that we're working with want to have power that's able to flow backwards from the grid under certain circumstances. And then another example of the type of interconnections that we do based on some of the different specifics that the customer asks for. This is what's called a 1.5 design, where you have a fully front of the meter connection at the top of the drawing to 500 kV feeds, independent power feeds, come into a 9-bus or a 9-breaker ring bus type of configuration, which provides highly reliable power to the customer. In any case where one of the tie lines goes out of service, the customer is still fed fully by power from the remaining in service tie line. And then just to mention some of the important studies that have to take place in order to make these type of interconnections work. So you can read the list of studies here, but some of the main ones that I would point out, necessary study and low deliverability studies are extremely important to understand what's the impact to the grid. So for instance, if you have a customer that's going to co-locate at a existing power station, and that power station's load is going to be taken off of the grid, these type of studies are necessary in order to ensure that there's no thermal overloads or other type of issues out on the grid that could require being addressed. And in cases where the customer's load is fully isolated from the grid, VAR support may need to be added to the design in order to address the customer's VAR support needs. I'd also mention on this page, on the right-hand side, capacity derating, and perhaps this is primarily a PJM type of an issue, but if you have a fully isolated load in the PJM market, it's required that you delist capacity for the unit, meaning you don't get a capacity payment from the grid at the same time that you are fully isolated from the grid for that customer. And the customer generally makes up for that capacity payment that folks within the PJM market would end up otherwise achieving. So some of the best practices mentioned there, IEEE standard 519, highly important to be coordinated with the data center or other large load, because load fluctuations can flow backwards to both the generator and the grid. And in some cases, there are examples where those type of fluctuations have had grid impacts. And so making sure that the customer actually has all of the equipment within their facility to make sure that they stay within the bounds of the IEEE standards. We also do parallel studies. It takes an exorbitant amount of time to get through PJM and other type of RTOs to have them review the impacts to the grid. There are companies that we utilize who are able within, a several week period to do the same amount of analysis that, might take a year within the PJM to get done. And what that does is it provides us the opportunity to know where are we going to have pinch points by the time that the RTO finally gets around to finishing their review and impact and understanding what the impacts to the grid might be. So we typically get out in front of these type of things in order to speed up the process. And then EPRI, Electric Power Research Institute's doing a ton of work these days in order to support understanding what are the impacts and best practices with co-locating large loads behind the meter or in front of the meter. And so, I just encourage folks as they're looking to potentially have these type of customers set up shop to be heavily tied in with EPRI in order to make sure that you're using what those best practices are. So with that, I will turn it over to Cy Moorty, and you'll get some additional perspective on large data centers
Thank,
and other kind of
thank
co-located
you,
loads.
Elliott.
Thank you, Elliott.
So we're gonna move to a grid operator perspective from customer and generator now.
Good morning, everyone. I would like to start off, over the past 2 days, I've heard the term co-located, and I just want to clarify from, I guess, my perspective and I guess the ERCOT perspective. Co-location does not necessarily mean with existing generation. For us, it's the same thing. Once we get a interconnection request, and if they have backup generation that could be synchronized to the grid, we treat it the same way as if you're interconnecting with existing generation. We have to go through all the studies. So when I'm talking about what we're doing in ERCOT, think of it in that term as it's not necessarily with existing generation. It's with backup generation that could be synchronized to the grid. I'll skip over this. I think there's been a lot of ERCOT folks talking about ERCOT. Yeah. What I'm going to talk over here is, I think we have heard a lot about the challenges of interconnection. The primary focus for a lot of the large loads is the interconnection process. I'm going to talk more from the market perspective, so that once this load is interconnected and operational, what is it that they can do? And so I'm just going to cover, like, operationally, once you're energized, the first thing is, what are the charges you face? And there are some credits. The next one is, I think I might skip over 2 because I think Karen and Elliott have already talked about what are the motivations. And I think that slide is just that. And the third one I'll talk is, what is the current construct we have for co-located? And here I'm saying whether it's a load bringing your own generation or co-locating with existing generation or backup generation, it's pretty much the same. And I think Karen talked a little bit about that. And then what lies ahead? And here I'll just give you a hint on some of the stuff we're working on in terms of a new participation, potentially a new participation model. Main thing is there is a lot of activity in the legislature this session, and we have to kind of wait and see what comes out of that. And of course, what's driving all this? It's the enormous large load interconnection request we're facing in ERCOT. So once you're energized, energy settlements, okay? So if you have generation, again, behind the meter, you have a single, might have multiple meters, but behind those meters, if you have generation and load, it doesn't matter what type of generation, whether it's existing generation, backup generation, or whatever it is. In ERCOT, the energy settlements are recorded on a 15-minute settlement interval, and it's the net as you measure it at the point of interconnection. It's the net, right? So if the load consumes 10 megawatt hours in a 15-minute settlement interval, and the generation produced 6 megawatt hours in that settlement interval, the load is charged for 4 megawatt hours. And that's something important to remember, because it doesn't matter when it occurred in that 15 minutes. You're just it's a net on that 15-minute basis. So that's, if it's a consumption, it's a charge. I know for the Googles and Amazons, they've got deep pockets, they don't care about this, but I'm a cheap guy, so I always look at the money. The next one is something called the load ratio share. So all loads in ERCOT have to pay for ancillary service. I mean, ERCOT procures ancillary services for reliability purposes on behalf of the load in ERCOT. Hence, the load must pay for it because ERCOT is revenue neutral. We pay money, we collect money. And that's based on the load ratio share. And again, the fundamental, there are different versions of load ratio share. There's a monthly load ratio share. There's a 15-minute settlement interval load ratio share. The more important one is the 15-minute because everything is built on that. So again, here, if you have a load co-located with generation, your share of the load for that 15-minute interval is your load or net load, if you have any. Let's assume the same case, you consumed 10 megawatt hours, but you generated 11 megawatt hours. You really don't have a load ratio share at that point because your net was a 1 megawatt hour injection into the grid. But if you were a net consumption in that 15-minute interval, it's your share of the total ERCOT load. And ERCOT, I mean, we are different from other ISOs where we pretty much get residential level meter information on a 15-minute basis, and we settle on that. So that's a pretty big part of ERCOT is the retail meter data that we get. And there are, based on that load ratio share calculations, you had to pay for ancillary service costs. There are other charges like the ERCOT fee that pays my salary. And there are other charges that if ERCOT does an out-of-market action, for example, it commits a unit to startup, and that's an out-of-market action, then that resource is eligible to get make-whole payments. And if there are any make-whole payments, that's distributed across all the loads on a load ratio share basis. There is some credit. So you get money back. So we run what's called a congestion revenue rights auction, where we auction off the capacity on these are really congestion hedges, run 5 years out, monthly, yearly, and all that. And any revenue collected from that is given back to the load on a load ratio share basis. So there are some credits over here, and there are charges. So these are some of the things that operationally, when a load is kind of running their business, these are the bills and credits they get. The other big part of this is the transmission cost allocation. In ERCOT, we have just a single postage stamp rate for everyone, every consumer in ERCOT. But there is a slight difference in how the different classes of consumers are treated. If you're 700 kilowatts peak demand or more, the way we calculate your share of T cost is based on what we call as the 4CP. It's the 4 coincident peaks. So for the months of June, July, August, and September, we look at a 15-minute settlement interval where the ERCOT peak was the highest and find out what your share was in that 15-minute settlement interval. And you get charged the T cost for the next year based on that. So this, I'm kind of going off track here, but I like to talk about this. This thing is pretty high. I put $50,000 per megawatt year there, but I think for every megawatt of your share, I think it's upwards of 60,000 megawatts per year. So that's a lot of money. And what this has resulted in is probably the largest unintentional demand response in the country. So everyone and their uncle, if they're 700 kilowatts or more, is gunning for this, if they can. So we've had, anecdotally, there was a steel plant, arc furnace, 1 year, they managed to hit all those 4 CP peaks and they reduced their consumption. They didn't have to pay any T cost the next year. So that's interesting. And this is one of the things that might be discussed at the legislative session this season. They're always talking about it, but nothing really comes out. So let's see what happens this year. So these are really the costs, right? You have cost and there is some credits over here. So operationally, these are what you're on the hook for. There will be other tariffs from your local wires company, the reactive tariff, peak demand, and all that kind of stuff. That's different. We don't deal with that. And we've already heard about what are the motivations for co-location. It's really the speed of interconnection. And here, when I talk about the speed of interconnection, it's really the infrastructure. You already have transmission there. So you don't have to go and procure equipment, switchgear and transformers and stuff like that. So what do we have as the current construct? It's a private use network. And what I'll do is I'll probably go to this slide. I guess what you see here is, I've given a simple example with a single point of interconnection. That's your settlement meter there, step-down transformer. You have a bunch of generation there. It could be solar, wind, or thermal. You have storage resources there. And this is your load, data center or industrial load. Typically, the private use networks, we've been having that for decades now, and these are primarily cogen facilities, but this is the construct we have even for data centers coming in. This could be, in this case, I've put these as market resources, but they can also be settlement only, where they don't really participate in the market. They can come on and shut down anytime they want to. But this is the general configuration, conceptual configuration for a private use network. All the settlements are done at the point of interconnection. That's what the meter reads. Now, if you have generation behind the meter and you want to monetize that, and this is where, I mean, last year around the same time, my boss kind of asked me, said, hey, we're getting a data center, 400 megawatt data center, and they have maybe 500 megawatts of backup gen. And the current private use network construct may not be provide enough incentive for them to register as a market resource. So they might come in as what we call settlement only, where they can come on and come off anytime they want to. ERCOT has no visibility into that. And that's what I've been working on. The main reason why they may not want to register as a market resource is because they can only sell their surplus capacity into the market after serving their native co-located load. So in the example I gave, if the load is 400 megawatts and the backup gen generally is sized a little higher, just in case there's some derations, if that's, say, 500 megawatts, the maximum they can sell to the market is 100 megawatts of their capacity, which means, they have to provide telemetry, they have to provide, their plans for the next 7 days, they have to submit outages, and they might say that's too much of a headache. And there's compliance risk for 100 megawatts. So that's may kind of, especially if it's backup generation, they may not be interested in participating in the market as a market resource. So what lies ahead now? There is a Senate Bill 6 in Texas, and they are talking about it's in general for large loads, but there is a section on co-located loads. And what I've written down here was from a version of the bill about 10 days ago. When I looked at it again yesterday, the language has changed significantly. And it's probably being voted on today in the Senate. But it's along these general lines. They're talking about what are the requirements. They're legislating some of the requirements, like almost like a grid code for large loads. So we'll see what comes out of it. And then this House may also make some modifications. But this is ongoing legislative activity that I would say that all the folks trying to put data centers in Texas need to be following. It's not just for co-located, it's primarily for large loads, but there is also a section there on co-location. And the bill kind of defines a large load as anything greater than 75 megawatts, 75 megawatts or higher. Now, what we are working on in ERCOT is more on how to incent, and primarily the backup generation. How do we incent them to register themselves as market resources? Because if I have a 500 megawatt backup generation that the ISO has no visibility into, we need to get them. We need to get them into the market. And some of the stuff that we are working on is finding out ways how they can sell their full capacity into the market. In the example I gave before, if there's 500 megawatts of backup generation, today they're only able to sell 100 megawatts. Is there a way that we can change some design so that they're able to sell 500 megawatts of their capacity, so that they can monetize their assets a little bit faster? Today, for a private use network, if you have a storage resource, they are not eligible for what we call as the wholesale storage load exemption. And what that gives is that the charging load of a battery, if you get wholesale storage load treatment, you don't have to pay a lot of the cost. You just have to pay the wholesale energy cost, but not the load ratio share charges. You don't have to pay T cost. So that, depending on how big the battery is, that could be significant. And then, of course, when we start talking about what other market changes we can make, is we can retain the feature of having the energy settlements as net at the point of interconnections. And I think that's all I had. So just to give you an example, I don't know if you can read this. That's 2,000, 4,000, 5,000, and then boom, it's just shooting up. And the different color codes over here are really telling you the level of the interconnection process. So the bottom one is that they're approved for energization, and then they're at the various levels of interconnection studies. And this is the total large load interconnection queue. The next one is the co-located. And I'll give you a number here. It's kind of plateaued out, and we're not sure why. Maybe policy uncertainty because there's some discussion going on at the legislature, or maybe the large loads have maxed out on where they can co-locate. So I'm not sure why this has happened. I was talking to our interconnection manager, and he pointed that out, saying it's kind of plateaued. Maybe after the session, when the policy are a bit clearer, maybe we'll start seeing an increase in that again. And this is something, again, I just wanted to point out we have an interim large load interconnection process, and this is what we're following. It's interim because it's not in the rules yet, in our protocols. And it's coming. So this is the process. So I think I'm not going to get into the details because I think our interconnection manager is probably going to talk about this tomorrow. I stole these slides from him. And this is another one I like. Just saying that, hey, I mean, we could improve. Our interconnection process is kind of like 3 to 6 years for building new transmission lines, not the interconnection process, but building new transmission lines. Should be improved, can be improved, I think. But we are better than the other guys. And that's all I have.
Thank you.
Hey, good morning, everybody. Thank you very much for your attention. After I was saying, used to be at a conference, the worst time to speak was right after lunch on the last day, but I think the morning after the reception is probably the new candidate. So I think if I'm successful, you're going to have more questions and no less after my presentation than you maybe feel you do at the start. It's probably more an idea and some numbers rather than a study or a lot of detail. So I'm going to talk about the area of high temperature industrial heat. Just to frame it, it's one of the largest sources of global emissions. It's about 30% of global emissions today, so incredibly significant. It hasn't got much attention at conferences like this because it's considered incredibly hard to abate. So we're talking about sectors like steel, cement, etc. And largely the view is being the technology isn't there or close to electrify or bring it. The other big challenge is just how cheap gas is. And when you're looking at, an alternative between an electrification of heat at high temperature or gas, it's a 1-to-1 fist fight. It's cost per kilowatt hour is what dominates the economics. You can do studies, you can put in capital costs, you can do all this, but these are very large volumes. The most simple way of looking at it is you need to be able to buy the electricity cheaper than the cost of gas, plus whatever carbon adders might be on gas in your market. So some things that are interesting, been around a good few years in lots of different parts of this industry, and you've probably all seen things go quiet for a long time and then suddenly it all changes quickly. The amount of progress in electrification of high temperature industrial heat in the last 3 years is remarkable. There are multiple new solutions that are they're just launching through TRL levels like I've never seen before for technologies of their scale and importance. And there's many different ones out there. There is also, and you'll see in money graphs, a lot of surplus of electricity becoming available in markets. So we're talking about areas where people have over-installed renewable resources for economics and there's curtailment available. So we're seeing many hours of the year where there's a lot of cheap electricity available at the wholesale level. But a few of the speakers have mentioned already, and it's been in other conferences, there's a lot of issues just around how that cost structure arrives to a customer and how the tariffs can distort it. So I want to just talk a little bit about the market distortions that were set up. I loved your case about a tariff on a typewriter. And that's what we run into almost everywhere. We don't, like the structure in ERCOT is very good where you're being charged. That would be very good for an industrial heat type of a demand because you could easily avoid the 40 peaks. But most of the time you're dealing with a tariff structure that was trying to incentivize really flat demand for a sort of world where you had capital intensive, whether it was nuclear generation, gas, transmission, distribution, very capital intensive assets. And if you could have a very flat demand, you were getting more capacity factor, you were getting more megawatt hours per year out of your installed capacity, and that made it more efficient. And that's what most of the demand tariffs, the T&D tariffs, they're structured to incentivize that, which is completely different to the economics and cost structure we have in the grid today. So I'll very quickly just show some graphs and numbers that are out there. So these are the IEA CO2 sectors by emission sectors and scenarios. This is their world energy outlook. And what you'll see on 2030 and 2050, they look at 3 scenarios from stated policies, essentially what's out there at the moment if nothing changes, a little bit more advanced where you get a bit more ambitious, and then a scenario where you head to net zero. And just looking at the stated policy one, because that's probably the one that's closest to the central scenario, you see they're expecting very little change in industrial carbon emissions. They're not seeing huge amounts of change coming. And I was at the slides, I think the session, I forget which one on Monday, but there was a lot of speakers showing their forecasts of how electricity demand was going to increase in the next 5-10 years. And most people were showing very significant increases, but it was coming from data centers, electrification of transport, little bit of heat pumps on the domestic side. I didn't see anyone talk about increased electricity consumption coming from electrification heat. And that's not just at this event. That's in any study I've looked at, in any scenario. And largely that's because of the assumption of where the technology is. So last year, the Fraunhofer Institute in Germany, very respected institute, went through quite a detailed assessment of what technology is available. And it's about a 50-page report. You'd scan it in 10 minutes and learn an awful lot, because it just goes through, here's different technologies, here's their state of maturity, and here's the sort of sectors they're suitable for. Their summary was that right now the technology is available to electrify 60% of industrial heat in the European Union. And European Union industrial heat is very similar. It's steel, it's the sectors are there, it's steel, pharma, cement. It's pretty much the same everywhere all over the world. And they expected that number to increase to 95% by 2035. So 95% of currently industrial heat demand could be electrified by 2035. And just look at that number at the bottom and remember it for maybe about, I know it's asking you to do a bit of work this early in the morning, but just remember that number for about 2 or 3 slides. That's about 2,000 terawatt hours of energy in the European Union 27. The Fraunhofer study is a little bit out of date. So the company I'm working here with is RedoxBlox, and I'll just give a 1 minute what the technology is, because this wasn't included in the Fraunhofer study, because we're at relatively early stage, but we're moving very quickly. We're at the sort of 100 kilowatt hour unit, and we'd aim to be at doing 20 megawatt hours next year. But it's instructive, and I would say that a lot of the technical parameters that we have, our competitors and other solutions would have very similar technical parameters, and that's what I think is interesting to this audience. So just indulge me for a moment. It's got a very fast charge, under 4 hours. So this unit can go from being essentially fully uncharged to fully charged with 4 hours of electricity consumption. That means you need about 2,000 hours a year of electricity to run 24/7 heat from this technology. A lot of our competitors, very similar ideas, similar technology. Inherently, there's an awful lot of storage in the heat sector. And there's a lot of storage in the technologies that are being used to electrify heat. Our solution gives us high temperatures up to about 1,500 degrees Celsius. And that's what's new, that a lot of the new technologies that are coming out are able to go to very high temperatures. And that's what's bringing sectors like cement, steel, aluminium, high temperature pharma processes into play, where previously they were not being looked at as potential electrification targets. Now they are. It's very high efficiency and very low capital cost. So I'll leave it there. If anyone is interested in learning more, happy to catch up with you over coffee. So it's a figure here on the global electricity demand and in the IEA, and their 2024 World Energy Outlook. It's a really good document. There's all published and a lot of data. I just put it here for completeness on this slide. It gives an idea of where electricity demand is all over the world. But the key takeaway I took was when you look through their forecasts, they're assuming very low levels of electrification of industrial heat. So just going back to the EU, and this is the net electricity generation in the European Union in 2022. And it was 2,700 terawatt hours. Now, how many people remember the number for total industrial heat that Fraunhofer expects to be electrifiable by 2030? Any hands up, or is that too ambitious? 2,000 terawatt hours. So like, just think of those two numbers together over 10 years. And think where the European Union is strategically with gas supply and with commitments to net zero. So in the European Union, this is a very, very strong thing. In the US, there's a set of different economic drivers, so it may be slightly slower to move through, but some of the fundamental economics are moving very quickly in the favor of this. So to just think from, I'm originally a system operator guy, and I worked in ancillary services and procuring ramping and worrying about meeting demand curves and all that for way too many years. And I'd like to think, when I think about industrial electrification, a lot of people start talking about the 100% problem, and no one ever did that. Like when I went to, utility wind integration group, we talked about, can we get to maybe 5%, 10% electricity from wind on a system? But whenever we talk about industrial electrification, it's, oh, well, we can't do 100%. And yeah, but you're doing 0 now. So let's think about maybe just mentally a 50% scenario and what that would actually look like in practice. So for example, you would go into an existing industrial facility that's using gas to meet all their heat needs. You'd put in parallel an electrification solution. The capital costs, not insignificant, but when you do a long run economic study, they're almost irrelevant. They vanish out of your calculations. You can set it up so that you have complete dual fuel capability on that site. So if you get this situation where, for example, there's no wind or sun and it's high temperature, low temperature, very high demand, don't use electricity for 3 weeks. No problem. Burn gas. We're looking at 50% electrification over a year. So you can pick and choose the best hours of the year. And to get 50%, you can look at all sorts of studies that will come out of your system. But we're talking about maybe 2,000 hours a year where you want to be able to consume renewables. If you can do that, you're going to pretty much replace 50% of your heat need from gas to electricity and reduce the amount of carbon, because necessarily once you're doing it at that, you're going to be consuming renewable electricity almost everywhere. So in that sort of situation, the electricity, it has a lot of storage capability, and you have a dual fuel gas availability. You can turn off your electricity solution. You can just flip a switch, and it does absolutely no impact whatsoever on the host process or on the technology. And that's true for almost all the technologies in this space. The only limit is the speed of a control system. So we've demonstrated 50 millisecond response times, and most of those 50 milliseconds are just finding, oh, the frequency fell. Am I sure it's a frequency fall? Yes, it's a frequency fall. Cut off the load, and then the load is gone. It's incredibly highly controllable ramping. You can have this running at, assuming you've got a 50 megawatt unit, you could set it at 25. You can put it up to 50, down to 0, back up to 50 in under a second, and the load does not care. It's essentially just amount of energy in is getting transferred into heat, being stored, delivered out as heat when needed. You can do very long duration energy storage because the capital costs are relatively low. And if you think about like the 3-week example, if you look at it, if you've got a system where a lot of your demand is more controllable, it's energy storage rather than electricity storage. When we think of long duration storage, we're looking for something that can be converted into electricity, and that would be ideal. But if you can take something that is a base load consumer of electricity that is going to consume, every day of the year for their own reasons, like things like a steel mill or a cement mill, where you do not want that to ever cool down, because if it cools down, it's going to take you forever to get it back up and running. If you can take that as it's consuming on average, 500 megawatt hours a week. If you can run that for 3 weeks on gas without any problem, that's essentially delivered you that electricity demand back into the system for other users, and it's improving the overall system economics. The hardest part and the biggest one at scale is going to be the real-time network coordination. So it's going to be very, very efficient at being used at times when there is spare space in the network and there is good availability of wholesale cheap electricity. But when we start looking at this at the sort of scales that are possible, it is going to drive very significant network impacts. And we're going to have to be very, very thoughtful about how we think about co-location, how we think about the process of electrification, how we think about the real-time control. It's not just going to be about pick the cheapest wholesale price and we're going to go for it. We're going to have to be looking at the real-time network conditions and optimizing around that as well. So very quick deep dive into Ireland to maybe show some of the ones. There's a lot of very good published data. So the curve on the left shows the amount of expected res curtailment in 2030, about 15 terawatt hours. It's a huge number. And in Ireland, there's about 13 terawatt hours of industrial heat that's currently powered by fossil fuels. numbers, orders of magnitude are going to be similar in most places. Ireland would be at similar levels of res penetration to Texas, just for context. So looking at what that means on a sort of, these are curves that system operators will be looking at the whole time. So the curve in green at the top is your system demand. So essentially it's low at night, goes up during the day, goes a bit higher at tea time whenever he gets home, starts cooking dinner. The curve in yellow is the forecast wind. And they say whether it's forecast or actual is almost immaterial to what we're showing. So essentially what's happening is the wind, this is a fairly benign wind curve. It's going up as the day goes on, but unfortunately, when you start getting near the peak, the wind is falling off, which is challenging for a system operator. You've got the demand going up, the wind going down. You're trying to meet that with all the rest of your demand. And the curve in red is just the green minus the orange. This is what you're trying to meet with the remainder of your plant, so with your non-renewables. This is what you're left to serve. Now, imagine if we just take for a second, what if we'd electrified 50% of the electricity demand? So not 100, just 50% of the industrial demand that's currently powered by fossil fuels. What could we do to this? And we get this curve, which is a bit, I had to check the numbers and look at it many different times. And the assumption here is just, if we take 50% of the energy, that averages out at 685 megawatts an hour over the year, over the full year. This is a high wind day, so you may actually do this more on this day. So I didn't do that. I just said we're going to use the same amount every day just to keep the number sensible. The curve at the bottom is what the industrial heat demand looks like. And I've tried to do this to make the demand curve as flat as possible. I could have played with it a bit more, maybe got rid of that kink near the end a little bit. But the point is, with the scale, with 50% electrification of industrial demand, you can take a system that's on average doing maybe 50, 60% renewables and turn your net demand curve flat. It's a really remarkable opportunity. The other piece I'd say is at all those hours where you have very high res penetration and the industrial demand is up, you have huge amounts of frequency response availability and resource available to you. You have huge amounts of ramping flexibility. You can ramp that up, down, whatever you need to do. So just moving on a little bit to the economics, we're seeing, and many people have said, at the wholesale level, the price is improving. These are the percentage of hours where the day ahead price is below the cost of gas and CO2 in many different markets. It's getting better everywhere. This is just a basic idea from the IEA, again, I think, of where natural gas prices are relative to wholesale generation costs and final costs in all sorts of different markets. And what we see is that the generation cost is comparable to natural gas in many markets. There's more than enough hours of low-cost wholesale generation cost energy to make electrification economic, even in many parts of the US. So purely on an economic choice decision, the numbers work at the wholesale level. The real problem comes in with the legacy tariff structures. They're distorting when you particularly start looking at the impact at low numbers. So I did a quick just calculation. This is, a very, very simple tariff structure, and it's indicative of what you'd see everywhere. So very simple idea. You have an average generation cost of 13 cents a kilowatt hour, but your average energy generation over the lowest 4 hours per day is about 3 cents a kilowatt hour. And that would be typical in many markets with decent amounts of res. Your natural gas is about 5 cents a kilowatt hour. And other electricity charges, you'll see on the graph on the left, if you've got a base load demand, those numbers probably look around right. Most of your cost is the green. The orange is your charge per kilowatt, and I assume 50-50 charging per kilowatt hour and per kilowatt for transmission and distribution and market costs and recovering ancillary services and all the various other things. So it's a fairly, benign example. But what's interesting is if you say, okay, now I've got a demand and I'm only going to consume in the lowest 4-hour price periods every day, what does that pricing look like? And what's interesting is the per kilowatt element of your T&D and your market recovery charges dominate your costs. And they make you uneconomic relative to natural gas pretty much everywhere. So it's a remarkably, it used to be something that was, say, well, it's 10, 15%. But in this case, it's more than 50% of your total cost of electricity is the kilowatt element of your grid charges and other things. Now, the answer isn't to get rid of it. This needs a lot of thought and work. Electrifying at this scale is going to bring very large new peak demands in parts of your network, but the current structure is a bit too blunt and it's disincentivizing it completely. So there needs to be a good bit of thought around some of the themes around, can we co-locate this with new generation connections, particularly new large renewable generation connections? Can we do it to respond to the idea that this is flexible? If you start getting a situation where, you know, normally I have enough capacity on my grid for you as a load, but there's 10 hours a year when I don't, that's fine. Turn it off those 10 hours a year or reduce it or control it down. It's not a demand in the sense of this hotel that wants to, you know, if we all go upstairs and turn on the aircon, the electricity goes up. This is a demand that can be fully operationally controlled by a utility without any adverse impact to the long run economics or the host process. So just to wrap up, there's been remarkable recent technical process in electrification of industrial heat. I think it's the biggest thing coming at the industry that we're maybe not looking at hard enough. And that's understandable. It's just the speed and the amount of things that have changed in the last 2 or 3 years is just huge. It could deliver very significant global CO2 reductions. Look at a 50% electrification strategy. Don't get yourself in the trap of thinking we can't do 100%. Think what 50% with natural gas available in real time as a backup looks like. And lastly, I think we need to think and be very thoughtful about how we want to incentivize and charge for this. The network tariff elements are going to dominate the economics of electrification of industrial load at scale. So thank you, everybody.